During the last week, you have learned about local and wide area networks and also about routing protocols, in particular dynamic routing protocols. And in this tutorial, I would like to discuss in more detail the dynamic routing protocols, how they work and their types and their characteristics. There are three main classes of dynamic routing protocols. First of all, it's distance vector routing, for example, routing information protocol, or another one, enhanced interior gateway routing protocol. In the distance vector protocols, the routers exchange the information about distances to all the destination networks with each other, and based on this distance information, they build the best. They choose the next hop to every destination network. The second class is link state routing protocols. Different to the distance vector routing protocols, they, instead of exchanging the distance information, using these protocols, routers exchange the information about state of the links in the network. Therefore, each router using open shortest path first protocol or intermediate system to intermediate system protocol builds the graph of the network, the full map of the network, and applies the Dijkstra algorithm on this network to find the optimal path to every destination network. Finally, there is one more dynamic routing protocol class called path vector routing protocols. Namely the border gateway protocol, which is sometimes also classified as distance vector protocol, and this protocol tries to use the best of both distance vector and link state approaches. Let's now talk about in more details about distance vector routing and how it works and the specifics of this. First of all, when we talk about distance vector routing, we should know what is a distance. The distance could be a physical distance to the destination network, for example, in the number of hops or the number of routers between the source and destination network, and also it could be a metric or a cost of the route to the destination network. Such a metric could be a bandwidth to the destination network, or delay of the packets sent to this network, or other parameters, including again the number of hops or their combinations, like number of hops with bandwidth, with delay, and with some other parameters again. In using the distance vector routing protocol, each router stores a distance vector which consists of tuples destination, where for each destination network the router saves the distance. And the routers running the distance vector routing protocol exchange their distance vector, and therefore, so become information about all destination networks available in the network. Let's now talk about particular implementation of distance vector routing protocol, namely the routing information protocol. So, as I mentioned, it is a distance vector protocol, and it exchanges the distance vector for all known destinations, and it uses number of hops as a distance, and is based on the Bellman-Ford algorithm. To see how it works, we will take the sample network presented on this figure. However, so here we have 4 routers A, B, C, and D interconnected with each other, and these routers are obviously needed to connect these 4 client and destination networks, this, and this. However, to see how it works, we don't need to know the details on the destination networks, if they use switches or if hubs, and how many hosts are there. So for our example, we will convert this image to the following representation, where we have 4 routers A, B, C, and D, and our networks indicated with network prefixes. So the network connected with to the router A is has a prefix of 192.168.1.0. This network has a 20, and this too has a prefixes 192.168.30 and 192.168.40. Also, the routers have the networks to set up the connection between each other. It's the networks 192.168.10.0, 20.0, 30.0, and 40.0. So let's see how it works on this example. First of all, when routers are enabled, they add to the routing tables information about directly connected networks. For example, for router A has directly connected, has 3 networks directly connected: 192.168.1.0 and 10.0 and 30.0. So the router A will add the information about these networks into its routing table, and since they are directly connected, there is no next hop, so the router could directly forward the packet to this network, and the distance to this network should be set to 0 again, because they are directly connected. The same for the router B. It will add the 2 directly connected networks with the distance 0 to its routing table, and router C will add all 4 directly connected networks, and finally router D will add 3 networks with distance 0 that are directly connected to the router D. After this, the routers will start exchanging the information they have in their routing table, and let's have a look how they do this on the example of router A. So the router A, during the routing update step, should receive the routing tables of router C and router D. So these are the tables that were filled during the initialization of the routers, only with directly connected networks, and the information about these networks is now sent to the router A. So the router A will receive the routing table of the router C, and will start adding the routers to its own routing table. So the information about this network 192.168.3.0 is not existed in the routing table, so it will add it and also increase the hop count, the distance to this network as soon as he receives the information about this network from router C. So to reach this network, the router A should send the packet should follow through the router C. So it will be 1 hop more than router C has in its own routing table. The A will also set C as the next hop. In the same way, as soon as the information about this network is not presented in the routing table of the router A, it will add it, increasing the hop count by 1. However, for the next network, the router A has already the information about it in its routing table with the distance 0. and the network received from the router C should have the distance of one hop away. So the distance to the network reported by router C would be higher than the distance router A already have in its routing table. That's why the router A will ignore this update and will not update its routing table based on this information, and will continue to use a better route to this network that it has already in the routing table. And then it will add the last network. Later, or in parallel with this process, it will receive the updates from router D for the network containing the routing table of the router D, and will again install it in the similar way that routing that information about networks from the routing table of the router C. However, it will also ignore the information about this network as soon as the hop count of router A will be less than hop count the router D has plus 1. So 0 will be less than a number of hops to router D1 plus distance of router D0. 0 is less than 1, so the router A has already the better route to this network, and it will ignore this information. However, for the last route, the router A has the route to this network through the router C with hop count 1. And the same for the router D. The hop count is now equal, so the router A will add both of these routes to its routing table and will load balance the packets to this destination network. So part of the packets will be forwarded and go through the router C, and another part will be forwarded and go through the router D. Now, after all information between all routers was exchanged, the routing table of 4 routers will look as following. Router A will have the information from router C and D. Router B will have the information about about the networks directly connected to its only neighbor, router C. Router C will have the information it receives from routers A, B, and D. And finally, router D will have the information about networks directly connected to its neighbors one hop away, routers A and C. Then, after 30 seconds, the exchange of the routing tables should be repeated. However, one rule should be taken into account. Routers should not advertise a route to the neighbor from which it was received. Let's see why it's needed. Let's assume that the router C loses the connection to the network 192.168.3.0 and therefore removes it from its routing table and stops sending the updates. However, its neighbor, router A, already has the information in this network about this network that he received during the previous routing table exchange iteration. Then, during the next exchange iteration, the router A will send this information back to the router C. And as soon as router C doesn't have the information about this network in its routing table, it will of course accept this update and install this route from the router A with a hop count 2 instead of 0. During the next iteration, router C will again send the update to router A. However, router A will be forced to update it because if the C is entered here as the next hop, which means that if router A receives an update from router C with a higher hop count, with a higher distance, then probably something was changed in the topology behind the router C, and router A should also update its distance count. So it writes here 3. A distance of 2 from router C plus 1 hop to the router C. And then during the next iteration it sends this information again to router C, which again increases the distance count, and this situation is called count to infinity. However, if routers will not advertise a route to the neighbor from which it was received, so after the router C will remove this route from its routing table, and router A is not allowed to send the update back to the neighbor, to the router C from which it was received, then the router C will not install this incorrect route back to its routing table, and route A will later remove the route to this network as soon as no information is received from router C about this network. So after the next iteration, the routing table will look like this for the 4 routers. The router B will finally receive information about the networks that are located 2 hops away, about this network, about the network 192.168.1.0, and also this network. Router C will not, for the router C, nothing will change in its routing table because there is no networks that are located 2 hops away, and in the same way router A and router D will add the networks that are located 2 hops away. So now the network is converged, and every router can reach every destination in this network. For example, if router A needs to reach this network, it finds it in its routing table and sees that it should forward the packet to the router C and forwards it here. So the router C again looks for this network in its routing table and finds that it could reach this network through router B and sends the package to the router B. Finally, the router B has this network directly connected, and it just forwards the packet to the destination network. So we have looked how routing information protocol works, and however it of course has some limitations. First of all, the maximum supported hop count is 15, so RIP could not work in the networks where there are more than 15 hops between source and destination networks. It also has a slow convergence since updates are sent every 30 seconds. If we have a maximum hop count of 15, then it could take more than 7.5 minutes for the routers to receive an update from the network that is located 15 hop counts away. It also has count to infinity problem, which could be, however, avoided with the split horizon rule, but it also has a complicated handling of routing loops. Let's see it on the example. Let's let's have a look on which information is stored about this network on the routers C and D. So the C has information about this network 20 through the router B and with hop count 1. And routers A and D both have the same information to this network 192.168.2.0. I'll only write 20. Through the router C is the next hop with a hop count 2, and router D has the same entry in its routing table, so it could reach this network through router C with a hop count of 2. Now let's imagine that these routers during each update iteration they send to each other the content of routing table, including these 2 routes to this network. However, as soon as router C also sends this updates to them, they prefer the route received from router C as soon as it has a smaller hop count 1 than 2 that they have in their routing table. Of course, for router A, it's much easier to reach the destination network through router C than through router D with 1, 2, 3 hops. But now let's imagine what happens if this link breaks. So the router C stops sending updates to the routers D and A, and therefore both of these routers D and A, they accept the updates from each other. So the router D will install the route from the network from the router A with a hop count of 3, and router A will then install the route from advertised by router D with a hop count 3. And later then they both will send this information to the router C, which will install both of these routes. However, none of these 3 routers have a real path to the destination network. So the network will be converged in the wrong way. To avoid such a situation, there is a special technique called poison reverse. If link fails, the router C should not stop sending updates for the networks connected with through this link. Instead, he should send the updates with a link distance equal to infinity, with a distance equal to infinity to all routers. In this case, routers A and D will correctly update their routing tables and also set the distance to this network to infinity. So we have looked about, so due to these limitations of the routing information protocol, in the big networks, or when the fast convergence is important, or in the networks with a high amount of connections between routers and high amount of routing loops, people prefer to use link state routing protocols, which we will discuss in the next tutorial.